Hello there. Let's talk about bitwise operators. More specifically, let's talk about all of these operators that you see here. But before we get started with bitwise operators, I'm assuming that you're familiar with some concepts that would be important to understand bitwise operators well. For example, I'm assuming that you know number system, and more specifically binary and decimal number system, and conversion from binary to decimal and decimal to binary. Other than this, I'm also assuming that you're familiar with how Java stores integers, and I'm talking about both positive and negative integers. In this, the concept of one's complement and two's complement is important. Now, if you're familiar with these concepts, great. Please continue watching this video, and I'm sure you'll be able to grab everything that I'm going to discuss in a moment. If not, I have dedicated videos on all of these topics, which you can access by browsing the playlist on the channel or by clicking the card that would have appeared on the top right section of your screen. With that said and done, let's continue. Now, bitwise operators are not the first set of operators that we're going to discuss. We've talked about other operators as well. For example, plus and minus and logical and, where plus and minus belongs to arithmetic operators and logical and belongs to Boolean logical operators. So whenever we talk about operators, we're talking about some symbols like these, which takes some values and operates on them, which means they give some end result, right? For example, if I pass two values to plus, assuming that they are integers, plus will add them and give us the sum. Similarly, if I pass two values to logical AND, assuming that they are Boolean, logical AND will give me some end result, say some value, right? Which means that every operator works with some kind of operand. For example, if I pass Boolean to plus, it's not gonna work, right? Similarly, if I pass, let's say, string to logical AND, it is not going to work. And this brings up a question as to what kind of operands will bitwise operators work with. So to answer that question, bitwise operators works with integers. And when I say bitwise operators works with integers, it could either be a direct value in the code, or it could be a variable which holds an integer value. Now, if it is a direct value in the code, which is also called literal, it will be treated as int type. But if it is a variable, that variable could be either of byte type or short type or int type or long type, right? Now, if a byte or short variable is used, what Java will do is it will promote byte or short to int and then perform the operation. But if you use int, it will stay int, and if you use long, it will stay long. For example, if I take any bitwise operator, let's take a generic one. Let's say I'm taking OP, and this OP is one of the operators that is listed over here. And if I pass two values, say V1 and V2, what's going to happen is if the type of V1 is byte or short, it will internally be promoted to int. If it is int, it will stay int, and if it is long, it will stay long. So in short, for these three data types, V1 will be treated as int, and for long, it will be treated as long. Now, depending on whether it is being treated as int or long, the width will vary, right? We know that the width of int is 32 bits and of long is 64 bits. So if I take one of the bitwise operators and I pass two integer values, they will first of all be converted to int, or if it was originally long, it will stay long, and then they will be converted to binary system. And once V1 has been converted to binary and V2 has also been converted to binary, the operation will be applied. So this is how all of the operators in bitwise operator will work. Summarizing, when we use any of these operators and we pass some value, what's going to happen is if that value is of byte type or short type, they will be promoted to int. If it is of int type, it will remain int. If it is of long type, it will remain long. So in short, it will either be int type or long type internally. Now, once both V1 and V2 has been promoted to either int or has been left long, what will happen next is it will get converted to binary system, which means a combination of 0 and 1. And this will happen for both V1 and V2. Now, once this conversion has been done, the operator will be applied and the result will be given. And the result will also be in binary. But if we store it in a variable in Java or we print it, we will get it after that binary has been converted to decimal. So to conclude all of this, bitwise operator will work with integers, and you can pass integers either as binary or octal or hexadecimal or decimal, and you can use either byte, short, int or long. But ultimately what's going to happen is it will get converted either to int or it will stay long if it was originally long. And then if you had passed decimal or octal or hexadecimal, it will be converted to binary. Depending on the type it is converted to, the width will be either 32 or 64. And once that conversion to binary has happened, the operation will be applied. The result will also be binary, but when Java returns it back to you and you store it in a variable or print it, you will get decimal in the end. So with this clear, let's talk about the first set of operators, which will be these. Now, we are going to talk about bitwise AND, but we also have logical AND. We are also going to talk about bitwise OR and XOR, but we also have logical OR and XOR. And we are going to talk about bitwise NOT, and we also have logical unary NOT. So let's quickly recap whatever we had discussed about Boolean logical operators, and then we will continue our discussion about bitwise operators. And why is there a need to recap on the Boolean logical operators will become clear in a moment. So we know that Boolean logical operators will work with Boolean values, right? And it takes two operands, which means these are binary operators except the last one, which works with only one operand. Now, if we take two operands and considering that they can be Boolean, there are total of 4 combinations, right? True, 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 false, false, true, and false, false. So logical AND will give true if both are true. Otherwise, it will give false. Logical OR will give true if any one of them is true. Otherwise, it will give false. Now, logical XOR will give true if both the operands are different. If both are same, we will get false. And unary NOT will give us false if the operand was true, and it will give true if the operand was false. Now, the reason I discussed about logical operators while we were supposed to talk about binary operators is because, like logical operators works with two values, true and false, binary operators will ultimately work with only two values, 1 and 0. And if you are already familiar with this truth table, you can very easily use this to understand what's going to happen when we use the bitwise operators with 1 and 0. So first of all, let me quickly change A and B from true and false to 1 and 0 respectively. Now, if I consider the fact that bitwise operators will work with binary numbers, which means it will work with either 1 or 0, we will have 4 combinations, right? 1 in both, 1 in any one of them, and lastly 1 in none of them. Now, if we talk about the AND operator or the bitwise AND operator and not the logical AND one, what's going to happen is if we have 1 in both, bitwise AND will give us 1. If we have 1 in only one and the other one is 0, bitwise AND will give us 0. And the same thing will apply to this one and we will get 0. Over here also, we will get 0 because we have 0 in both. Similarly, if we talk about the bitwise OR, the behavior will be similar to what it was with logical OR. If we have even 1, 1, the result will be 1. And that is why the first one will be 1. For the second one, we have 1 and 0. So the result will be 1. For the third one, we have 0 and 1. So here also result will be 1. Last one, we have 0 and 0. And the result will be 0. Similarly with XOR, what's going to happen is we will get 1 if both are different. So we'll get 1 and 1 here, but we will get 0 in the other two cases because both are same. Now coming to NOT, we will first of all need to change this because bitwise NOT is written this way and not this way. So let's put the tilde symbol. And now, similar to unary NOT, what's going to happen is if the operand is 1, bitwise NOT will give 0. And if the operand is 0, bitwise NOT will give 1. So this is all about bitwise operators. More specifically, bitwise AND, bitwise OR, bitwise XOR, and bitwise NOT. So the truth table that we had discussed in Boolean logical operators in a way holds here as well. The only difference is all of the true that we had got replaced with 1, and all of the false that we had got replaced with 0. But please don't confuse that true in Java means 1 and false in Java means 0. This is not the case. True in Java is true, false in Java is false, 1 is 1 and 0 is 0. They cannot be used interchangeably like in some other languages, for example, C. Now with this clear, let's take some example and let's try to apply all of these operators on some numbers. Now let's consider, say, 42 and 15. So 42 and 15 are in decimal number system, right? Which means considering Java, they will be treated as int. If we had stored them in a variable, for example, say byte n1 is equal to 42 and byte n2 is equal to 15, they would internally get promoted to int. But ultimately, the conclusion is these will be treated as int. Now, with that clear, what is the next step? The next step is to convert these in binary, right? So since they will be treated as int, we will have 32 slots for the binary conversion. So let me quickly draw those 32 slots. First of all, for 42. All right, it's pretty difficult to fit 32 spaces over here. And that is why what I have done finally is kept 10 spaces, which I know will be sufficient for 42 for sure. And for the rest, I've just put dots and 31 over here so that you understand that it is a space with 32 slots. Now with that clear, let's quickly convert 42 to binary. For that, what we can do is we can take 42 and check out of all of these positions, which is the largest one that we can fill first. For example, if I take 6, 2 to the power 6 is 64, but 64 is greater than 42, which means 6 will have 0, right? But if I take 5, 2 to the power 5 is 32, which is less than 42. So what I can do is I can put 1 over here, which means I have put 32 already, and now I'm left with 10. For 10, which is the largest slot that we can fill. We cannot fill 4 because 2 to the power 4 is 16, but we can fill 3 for sure, right? So we will put 1 over here, and that means now we are left with 2. For 2, we can fill 1, and the remaining one will have zeros in them, right? So this is a quick way to convert decimal to binary without the repeated division method. Similarly, let me draw slots for 15 and let's fill that as well. For 15, if we go for the same approach, what's going to happen is the largest slot that I can fill out of all of these is 3, right? So 2 to the power 3 is 8. So we're done with 8 out of 15 and we are left with 7. And then we can fill this one. So we'll be done with 4. We'll be left with 3. Then we can fill these two and we'll be done with 15. So ultimately, we have converted both 42 and 15 into binary. Now let's understand how will each of these operators be applied on them. So let's say, first of all, we are going for AND. Now what's going to happen over here is all of these empty ones will have zeros in them. So for the purpose of AND, what we can do is from 31 all the way up to 6, it will have 0 in both of them, right? So we can say it will have zeros all the way up to 6. Now, if we take position 5, what do we see over here? We have 1 here and we have 0 here. And what do we know about AND? We know that if we use bitwise and we have 1 in the first one and 0 in the second one, it will give us 0, right? So what we can do is we can put 0. If we now consider position 4, we'll have 0 in both, so we can put 0. Now we'll consider position 3. We will have 1 in both. So what's going to happen is we will put 1. And now we will have position 2. We have 0 in one and 1 in the other one. So we will say 0. Lastly, we have 1 in both the cases at position 1. So the result will be 1. and this one will be 0. So lastly, we'll say 1 here and 0 here. And this is the result of performing bitwise AND on 42 and 15. But this is in binary. Let's quickly convert it to decimal. So to convert in decimal, we can do this. 2 to the power 1 is 2 and 2 to the power 3 is 8. If we go for 8 plus 2, we are going to get 10, which means if we go for 42 bitwise and 15, we will get 10 as the answer, right? Similarly, let's quickly perform bitwise OR on 42 and 15 and let's see what the answer is. Now, similar to AND, it will be 0 for all of the positions starting from 31 all the way up to 6. So we can jot that down. Now, what's going to happen for positions 5 all the way up to 0? Let's analyze. Position 5, we have a 1 over here, so it will be 1. Position 4, we have 0 in both, so it will be 0. Position 3, we have a 1, so it will be 1. Position 2, we have a 0 here, but 1 over here, so it will be 1 here as well. Position 1, we will have 1, and position 0, we will have 1. So ultimately, the last 6 bits will be 1, 0, 1, 1, 1, 1. So let us put that down here, 1, 0, 1, 1, 1, 1. Now, if we convert this in decimal, what will we get? This will be 2 power 0, which is 1. This is 2 power 1, which is 2. This is 2 power 3, which is 8. This is 2 power 4, which is 16. And this is, oh, there's a mistake. Let's restart. 2 power 0 is 1. 2 power 1 is 2. 2 power 2 is 4. 2 power 3 is 8. 2 power 4 multiplied with 0 will be 0. So we will skip that and we will reach 2 power 5, which is 32. Adding all of this, what are we going to get? We're going to get 32 plus 8, 40 plus 4, 44, then 2, 46, and then 1, 47. So that means if we go for 42 bitwise or 15, we are going to get 47. Now let's also check what will be the output of 42 bitwise XOR 15 and 42 actually not 42 and not 15. For that, what am I going to do is, instead of dealing with all of these 32 bits, I'm only going to take the positions 0 to 8 while discarding 9 to 31 because they anyway have 0, so they won't have any effect on our answer. So what I've done is I've taken position 0 to 7, not position 0 to 8, and I've discarded 8 all the way up to 31. So with this done, let's apply bitwise XOR first, and then we will apply the NOT operator on each of these. So for XOR, what do we know? Well, if we check this table, we know that XOR will give us 1 if both the operands have different values. But if both the operands have same value, we will get 0. So applying that over here, the first one have got same value, will get 0. Then this one also has the same value, so 0. Different values will get 1, same value 0, same value 0, different value 1, same value 0, and different value 1. And if we calculate the binary to decimal conversion, we will get 2 to the power 0 here, and then 2 to the power 2. Then this is 3, 4, 5. So 2 to the power 5. And we will ultimately have 2 power 5, which is 32, 2 power 2, which is 4, and 2 power 0, which is 1. And this will give us 37. So if we go for 42 XOR 15, we will get 37. Now let's find the NOT of 42. So we have got 00, it will be 11. Then we have 10, it will be 01. Then we have 1010. So we'll have 0101. And similarly for 15, we will have 0000. So we'll have 1111. Then we have 1111. We'll have 0000. Now, if you're familiar with how Java stores integers internally, you would know that the last bit, which is this one, determines the sign. And if it contains 1, it means it is a negative number. 0 means it is a positive number. This, by the way, is called the MSB, or the most significant bit. Now, I know that we have trimmed down to only 8 bits where we originally had 32 bits. But even if we take all the 32 bits, what would have happened is we would have extra ones towards the left, and the answer would have remained the same. So assuming that, let's find which number is this representing and which number is this representing. So we will quickly jot the first number down. Now, since this is a negative number, which we can conclude by the fact that MSB contains 1, it means that it is in 2's complement. And to solve for 2's complement, the first thing that we will have to do is invert the bits, which means we'll go for 0, 0, 1, 0, 1, 0, 1, 0. So inverting the bits basically means convert 1 to 0 and 0 to 1. Now, once the inversion of bits has been done, we add 1 to this. So we are adding 1 to the bits that we got after inverting the original one. So we'll have 0 plus 1, 1, then we will have 1 here, then 0, and then 1, and then 0, and then 1, and then 0, and 0. Now, which decimal number is this binary number representing? So this is 2 power 0, this is 2 power 1, this is 2 power 2, 2 power 3, 2 power 4, and 2 power 5. 2 power 0 is 1. 2 power 1 is 2. 2 power 2 multiplied with 0 will be 0. So we'll put 0 over here. 2 power 3 will be 8. 2 power 4 multiplied with 0 will be 0. And 2 power 5 multiplied with 1 is going to be 32. So if we add them up, we'll get 32 plus 8, 40, 42, and 43. So what do we get ultimately? We get 43. Now, this 43 is a result of what we have here. And we got this by adding 1 to this, right? And we got this by inverting the bits of this, which was the original number in binary number system for which we were trying to find the decimal conversion. Now, since the original number was negative, what are we going to do is we're going to put minus over here, which means that if we go for not 42, where the not that I'm talking about is the bitwise not operator, we're going to get minus 43. Now, similarly, you can solve for 15 as well. And I'm not going to take up 15, and I highly recommend that you do it. You take 15, which you know can be represented this way in binary number system. And then you try to find the not of it, as in apply bitwise not operator to 15 and see what is the result that you're getting. So this is how we can use the bitwise AND, bitwise OR, bitwise XOR, and the bitwise NOT operator. Now with this clear, let's do the same thing in IntelliJ, as in let's take two variables, assign 42 to one and 15 to the other one, and let's perform the bitwise operators and see what is the output that we're getting. So for that, let's first of all have a byte variable called num1 where we will store 42, and 42 can be stored in byte variable, right? Because the range of byte variable is minus 128 to 127, and 42 falls within that range. Then we'll take num2, we'll have 15 over here. Now what am I going to do is I'm going to have a variable result, and I'm going to say num1 bitwise and num2. Now we are getting an error over here, and that is because we have not specified the type of result. But what should the type of result be? As we know that if we take byte or short, it will get promoted to int, and then the bitwise operator will be applied. And the result that we will get will also be int. So let's say I have int here, and as you can see, the error vanished. Now if I go for sout result and I run the code, we get 10, and this is what we got when we solved this here. Now let's apply bitwise OR and XOR and see if we get 47 and 37 respectively or not. So I've changed the name from result to and result so that I can keep it and use other operators also. So let me rename this to OR result and rename this to XOR result. Let's change the operator as well. Now let's copy this println statement, paste it, and say OR result here and XOR result here. And let's run the code. So we got 47 and 37. And that's exactly what we got here. Now let's apply the bitwise NOT on 42 and see if we get minus 43 or not. So I'll have a variable say int not num1, and I'll say, or let's name it not num1 result, and I'll say not num1. Now let's copy this println statement, paste it here, and pass not num1 result, and let's run the code. And we get -43, which is what we expected. For num2, I'm not going to perform the not operator on num2 because I want you to do it. And I want you to write the code and check if whatever you did using pen and paper is giving you the same result that the Java code would have given. Now, before we proceed, there's another important point which I wanted to demonstrate. You already know that if we use byte or short, it will get promoted to int and then the bitwise operator will be applied. But that is something we have discussed in theory. Let's see if I use byte or short over here instead of int for and result, we are getting any errors or not. So if I say byte here, it is giving an error, right? And if I hover on this, it says required type byte, but provided int, which means because the and result variable is of byte type, it was expecting a byte value. But what we have done is we have provided an int value. And if I still run the code, we will get an error saying possible lossy conversion from int to byte. Now, this in short means that we cannot assign an int value to a byte variable. We've not discussed the reason so far, and we are going to do it, but that will happen in a separate video. So with this, we're done with 4 bitwise operators. So we're done with not, and, or, and XOR. Next, let's focus our attention to these 3 operators, and we will discuss them one by one, starting with this. Now, this operator is called the right shift operator. Now, as this is a bitwise operator, everything that we had discussed over here, that is byte being promoted to int and short being promoted to int and converting the operand to binary and then performing the operation, holds true for the right shift operator as well. Now, let's take an example and see how right shift operator works. So the general format is this: value, right shift, and num. Let's understand this, but with the help of an example. Let's say value is 48 and let's say num is 2. What's going to happen is the right shift operator will apply on 48 and it will shift the bits of 48 towards the right by 2. Let's see how it happens. First of all, let's convert 48 to binary, and we will use the same trick that we had discussed a few minutes ago. For 48, assuming we have 8 slots, although internally it will use 32 or 64 slots depending on whether it got promoted to int or it was originally long. So assuming only 8 bits here, which is the first value from left that we can fill here. We cannot fill 6 because 2 to the power 6 is 64, but we can fill 5, right? So we'll say 1 over here, which means 32 gone, and now we are left with 16. For 16, we'll say 1 over here, and we will be done. All of the remaining will be 0. Now, if I say 48 right shift 2, what's going to happen is the bits that we have over here will get shifted towards the right by 2 spaces, which means whatever is at 7 will go to 5, whatever is at 6 will go to 4. Similarly, 5 to 3, 4 to 2, 3 to 1, and 2 to 0. Now, what will happen with the bits at 1 and 0? Well, they will get discarded. So shifting the bits towards the right by 2 bits or 2 spaces will mean that we will lose these 2 bits. Now I said that whatever is at 7 will go to 5 and whatever is at 6 will now go to 4, which means 7 and 6 are now empty. So what will be there? Since they are empty, they will have zeros. Now what will be at 5? Well, at 5, we will have whatever was at 7. So we will have 0. At 4, we will have whatever was at 6. So we'll have 0 again. At 3, we will have whatever was at 5. So 1. 2, we will have whatever was at 4. So we will have 1. Then at 1, whatever at 3, which means 0. And at 0, whatever was at 2, which means 0. Now, if I calculate, what are we going to get? Well, this is at position 2 and this is at position 3, which means we have got 2 square plus 2 cube, which is equal to 8 plus 4, which is equal to 12. Which means if I go for 48, right shift 2, I'm going to get 12. So again, if we use the right shift operator, what's the syntax? The syntax is value, that is the operand on which you want to perform right shift on, and the number, that is the number of bits you want to shift to the right. Here we had taken 48 right shift 2, which means in the binary representation of 48, all of the bits will get shifted to the right by 2 spaces. And that means the bits in the first 2 slots from the right will get lost, and the bits in the last 2 slots from the right will be filled with zeros. And this will ultimately give us 12. Now let's take one more example and see what will happen if we apply right shift and say we shift by 1. Let's say we have 33 and we want to right shift by 1. Now 33 can be represented in binary this way. Again, there will be 32 slots or spaces when this is done in Java, but for keeping it short, I'm taking only 8, because anyway, all of these bits towards the left, which I have not taken, will have 0. So the result is going to be unchanged. Now, this is how 33 is represented. And if I want to shift it to right by 1, what's going to happen is this 1 will get discarded and this will come over here. So 0, this is going to come here. So 0, 0, 0, 1, 0, 0, and this will be 0. Now there's only 1 over here. So what's this in decimal? This is 16. So 33 right shift 1 will give us 16. Now can you observe something over here? We have 33 right shift 1 that gave us 16. So is 16 also equal to 33 by 2? Yes. Similarly, I have 48 right shift 2 and that gave us 12. So can I say 48 by 4? Will I get 12 if I go for 48 by 4? Yes, we will, right? Now, if I take 33 by 2, can I write this as 33 by 2 power 0? And if I take 48 by 4, can I write 48 by 2 square? Similarly, if I have 33 by 2 power 0 and knowing that I right shifted by 1 place, can I say 33 by 2 to the power num, where I'm talking about this num. Similarly, over here for 48 by 2 square, can I say 48 by 2 power num? We can, right? So what is all of this telling us? This is telling us that if we go for value right shift num, what are we going to get is a new value. And that new value will be equal to the original value divided by 2 power num. And over here, the remainder is discarded, right? Because if you see 33 by 2 is 16 with a remainder of 1. We got only 16. And this is a neat little trick that you can use to perform divisions faster. But of course, the number you're dividing with should be a power of 2. So this is what happens when you right shift a positive number by a certain number of space. Let's see what happens when you right shift a negative number by a certain number of space. For that, let's take -8 as an example. And let's say we want to right shift -8 by 1. So first of all, we will have to represent -8 in binary. So for representing -8 in binary, what we will have to do is we'll have to start with just 8. And we'll have to find its binary equivalent, which we know is 000 1 00 00. And over here, I'm again taking 8 bits, but the result is going to be unchanged even if you take 32 or 64 bits. Now, once we have 8, we'll have to find 1's complement, and 1's complement is inverting the bits. So zeros to 1's and 1's to zeros. Once this is done, we'll have to add 1 to the 1's complement. So if I add 1, what are we going to get? We will have 1 1 0 carry over of 1, 1 1 0 carry over of 1, 1 1 0 carry over of 1, and 1 over here. And then we'll take all of these 1 down here. So we ultimately have 1 1 1 1 1 0 0. And this is -8 represented in binary. Now, once we have -8 and we want to shift it by 1, what's going to happen? Something similar that happened in this case. Let's see. So let's put 8 spaces here and we are shifting to the right by 1, which means this will get lost. This will come over here. This will be here. This will be here, and so on till this bit, which is here. Now, what will happen to this bit, which is now vacant because whatever was here got shifted to the right by one space? Will it be filled with 0? No. So whenever a bit gets vacant, it gets filled by whatever is there at the MSB. That is the most significant bit. And in this, the MSB was 1, which means this empty bit will get filled with 1. And this is the same reason because of which I said that when we go for 48, right shift 2, where 48 can be represented this way in binary, and we shift the bits to the right by 2, these two spaces got vacant, right? And we had filled them with 0. And the reason we had filled them with 0 was not just because they got vacant, it was because the MSB had 0. So when you shift to the right by, say, num number of spaces or k number of spaces, what's going to happen is the rightmost k bits will get dropped and the leftmost k bits will become vacant. And when they become vacant, you fill them with something. And that something is determined by whatever is there in the MSB or the most significant bit. If it is 0, you'll put 0 there. If it is 1, you will put 1 over there. Now, let's find out what this number is. So this is 11111100. Now, as you can see, the MSB has got 1, which means this is a negative number. And if it is a negative number, it means that it is represented in 2's complement. And to convert it to decimal, we will first of all have to invert the bits, which means we'll need to find the ones complement, which is 00, 00, 00, 11. And then we will have to add 1 to one's complement. We will get 1, 1, 0, 1 carryover, 1, 1, 0, 1 carryover, and all of these will be 0. Now this is 4, right? Because we have got 1 at position 2. So 2 to the power 2, 4. So what did we get ultimately? We got 4. What did we start off? We started off with this. This was a negative number because there's a 1 in MSB. So we will put a minus sign, which means if we go for -8, right shift 1, we get -4. Now there's another thing that we had discussed about right shift, which is going for value right shift num is equivalent to saying value divided by 2 to the power num. So let's check if that holds here as well. So here we have got -8, and if we divide this by 2 power num, which is 1, what should we get? We should get -4, and which is what we are getting, which means the generalization that we did over here for the new value that we get when we go for value right shift num holds both for positive and negative integers. Now let's come back to IntelliJ, fix this error, and let's perform right shift on a random number. So let's choose 42 and 15 both. Let's say we go for a variable called num1 right shift say 1, which means I'm going for this num1 right shift 1. If I print the value of num1 right shift 1 variable, what do I expect? So we have 42 and we are right shifting by 1, which means we will have 42 divided by 2 power 1, right? Which is 2. So we will have 21. So let's run the code. And we've got 21. Similarly, if I do the same thing with num2, let's change the name of the variable first and let's use num2 here, which is 15. What should I get? I should get 7. So if I run the code, I get 21. Okay, that's because the println statement on line number 19 has the wrong variable name. So if I run the code again, I get 7. Similarly, if I change this to num1 right shift 2, for example, it will be 42 by 2 square, which is 4. And I'm going to get 10. So if I run the code now, the second last line should be 10. And that's exactly what we got. So this is how the right shift operator works. So what did we see in right shift? In right shift, we shift the bits to the right by certain number of spaces. And what happens is the rightmost bits get lost and the leftmost bit gets vacant. And when they get vacant, we fill them with whatever was originally there in the MSB. So in short, if we have a positive number, right shifting will give us a positive number because positive number will have 0 in MSB and we fill the empty space with 0 only. But if we had a negative number to begin with, right shifting will give us a negative number, because a negative number will have 1 to begin with, and when we shift and the space becomes vacant, we put 1 over here, because that's what was there in MSB, right? And that means that the right shift operator will preserve whatever was the sign, which means if it was a positive number, we will have positive. If it was negative number, we will have negative. But there's another operator which does what right shift does, but without preserving the sign. And that is this operator. This is called unsigned right shift. Now there's only one difference between the unsigned right shift and the right shift. That is, right shift will preserve the sign, whereas unsigned right shift will not preserve the sign, which means if you go for, let's say, value unsigned right shift num, what's going to happen is if we have some bits, num number of bits will get lost, right? And num number of bits towards the left will get vacant. If you would have used right shift, what would have happened? These would have been filled by whatever was there in MSB. So if MSB is 1, it will have 1. If MSB is 0, it will have 0, right? With unsigned right shift, however, what's going to happen is the vacant bits will get filled with zeros only. So let's come back to IntelliJ and see unsigned right shift in action. But before that, what I think I should do is take a negative number and apply the right shift operation. So let's say I take negative number in the variable called negative number, and let's say I put -1. And what I will do now is I'll say right shift negative number, and I'll say negative number right shift 1. And if I go for S out on the right shift negative number, as in I print the value of right shift negative number variable, what should the last line of output be? Well, it is -1. And it is because right shifting -1 by 1 bit will lead to -1 divided by 2. And this will give us -1. Now you'll get the same result, of course, even if you convert -1 to binary and then perform the right shift operation and convert the result back to decimal. But what's going to happen if I say go for unsigned right shift negative number, and I take this, put it here, and instead of going for this, I go for unsigned right shift and I print the value as well. So if I copy the variable name, paste it here, let's run the code and see the output. The output is 2147483647. And this number seems familiar, right? It is because this is the maximum value that an integer variable in Java can hold. Now, let's understand why did -1 unsigned right shift by 1 give this. For that, what we will have to do first of all is we will have to convert -1 to binary. And for that, the steps are pretty simple. We take -1 without the sign, which means we take only 1. And 1 in binary is all 0 and 1 at the end. Now over here, I'm taking all the 32 bits, and this is important. We will get to know why in a moment. Now what's going to happen next? So we started with 1. Now we'll have to invert the bits, which means we're going to have all of these change to 1 and the last one will be 0. So I'll say 31 1 and lastly 0. Then I'll have to add 1 to it. So if I add 1, what's going to happen? We'll have 1 over here and all of these will be 1. So we will have 32 ones. Now think about it this way. The width of int is 32, which means there are 32 bits in total and all of them are filled with 1, which means this will give the maximum value that 32 bits can hold. And the maximum value that 32 bits can hold is also the maximum value that an int variable can hold, because an int variable is 32 bits wide. And that is why we're getting 2147483647, which is also the maximum value of an integer. And to check that, this is what we can do. We can go for system.out.println and we can say integer dot max value. This max value constant is supposed to give the maximum value of int in Java. And if I run the code, the last two lines of output should be same, and they are, which we can prove by going for a find operation. If I find this, I get two occurrences, right? So this is about the unsigned write shift. Now in the example so far, I had taken only 8 bits, and that was because I knew that the example that I am taking will yield the same result if I take 8 bits or 32 bits. And so I took 8 bit to make the discussion quicker, but still 100% accurate. But if you use these operators in the Java code, all of the operations will be done on either 32 bits or 64 bits, depending on whether you were using byte or short and they got promoted to int, or you started with int and that remained int, or you started with long and that remained long. So please keep that in mind while writing the code and try running it. Now with that clear, let's talk about this operator. And you might have guessed the name already. This is the left shift operator. The syntax is similar to right shift. It is value, left shift, num. So we specify the value which we want to left shift on by a certain number. So let's see, how can we use this? Let's take a positive number to start off. Let's say I take 18 and I left shift by 2. So first of all, let's represent 18 in 8 bits only. And that can be done by putting a 1 here and a 1 here and 0 in all the other spaces. So what will happen if we left shift this by 2? What's going to happen is whatever is at 0 will be at 2. So I will have 0 over here. Whatever was at 1 will be at 3. So 1 over here. 2 will go to 4. So 0 here. 3 will go to 5. So 0 here. 4 will go to 6. So 1 over here. 5 will go to 7. So 0 over here. And these two bits will get lost. And we've got two vacant spaces and they will be filled with 0. Now, unlike the right shift operator, where the vacant spaces which were on the left were filled with whatever was there in MSB, over here, the vacant space will always be filled with 0. So considering that, this is what we will get when we go for 18 left shift 2. Now, if I evaluate this, what are we going to get? We've got two ones, one at position 6, another one at position 3. So this is 64 plus 8, which is 72. So 18 left shift 2 is 72. Now let's do something similar but with a negative number. Let's take minus 18 and we go for left shift 2. So first of all, for finding minus 18, we'll have to take 18 and we will have to find its binary equivalent, which is this. However, if I take only 8 bits over here, while knowing that internally it will be either 32 or 64 bits, the result that I will get at the end may be wrong. I'll tell you why. But before that, let me invert the bits and find the ones complement. This will be 1 1 1 0 1 1 0 1. And then let's quickly add 1 and find the 2's complement. So it is 1 1 0, 1 carried over. We'll have 1, then 1 1 0 1 1 1. So what is minus 18 ultimately? It is 1 1 1 0 1 1 0. So let's say I want to shift it to the left by 2. What's going to happen? These two bits will get lost, right? This 1 will be here at position 7. This 0 will be here at position 6. These three ones will be at position 5, 4, and 3, right? And this one will be at position 2, as in the 0 over here. And here we will get zeros. So this is what the left shift will give us, correct? Now what did we get was this 0 0 1 1 0 1. And if I convert this to decimal, let's see what do we get. We have 1 0 1 1 0 0. Over here, this is a negative number because the MSB is 1. So what we will have to do is, first of all, invert it. We will get 0 1 0 0 0 1 1 1. And then we will have to add 1 to it. So we will get 1 1 0 1 carry, 1 1 0 1 carry, 1 1 0 1 carry, 1 0 0 1 0. Now what is this number? This is 2 power 0 1 2 3 4 5 6. So we will have 2 power 6, which is 64 plus 8. We will have 72. So this gave us 72. We started off with this number, right? And since this was negative, the result would be minus 72. Minus 18 left shift 2 will give us minus 72. But what if instead of left shifting by 2, we would have left shifted by 3? So what would have happened is we would have lost these 3 bits, right? And whatever was here would have been here at 7th position. These ones would have taken 6, 5, and 4. This 0 would have taken 3, and 2, 1, and 0 would have been filled with zeros. Now, do you see what changed over here? This is a negative number, and if we left shift, we should still get negative number. But what happened over here was the MSB is 0. So our calculation will give us a positive number. But in reality, if we do this in Java, we will see that minus 18 left shift by 3 will give us a negative number. So let's see this in action. Let's say over here, what I'm going to do first of all is comment all of this out so that the output only contains the relevant one. Now let's take num over here, whose value is say 18. And what am I going to do is straight up, I'm going to print num left shift 2. And if I run the code, what do I expect? 72. And that's what we got, right? Now if I change this to minus 18 and I run the code, I get minus 72. But if I keep num as minus 18 and if I change this to num left shift 3, we saw that taking just 8 bits instead of 32 or 64 will give a positive number. But let's run the code and see if we are getting a positive number or a negative number. And if I run the code, I get minus 144, which is a negative number, which is the correct one, right? The reason this would have given us a positive number is because we took only 8 bits to represent minus 18, but that is not the case when Java does it. It represents minus 18 either in 32 bits or 64 bits. So summarizing whatever we have discussed about right shift, left shift, and unsigned right shift, it is that the general form is this value and whatever operator we take from here and num. Right shift operator will shift the bits to the right. Left shift operator will shift the bits to the left. Now, when the bits are shifted to the right, what happens is the leftmost bits become vacant, right? And in that case, whatever was there in MSB is put over here. So if it was 1, we will put 1. If it was 0, it will put 0. For the left shift, however, what happens is the bits on the right gets vacant. And over here, this is always filled with 0. Now, regarding the unsigned right shift, which is this operator, when we shift bits to the right, the left bits will become vacant, right? If we use just the right shift, it will fill this with whatever was there in MSB. But if we use unsigned right shift, it will always fill it with 0. Another thing that we discussed was these operators will be used either with int or long. And not just these operators, all of the bitwise operators will operate either on int or long. So if we had byte to begin with, it will be promoted to int, which means if we had used just 8 bits, it will ultimately get stored in 32 bits of space. So what's going to happen is you had bits from 0 to 7, it will get converted to be from 0 all the way up to 31, right? Because it will be using int. Now, although the operation will be performed on int, but if you still want the byte representation itself, what you can do is you can cast it to byte, which means what you can do here is, let's say you had byte a is equal to some number, say 64, right? And what you did was you went for a left shift 2. Now you know that the left shift operator will work with int. So what you did was you stored it in a variable called I, right? So if you print I or you use I, you will be using all of the 32 bits. But if you want to use only the 8 bits because you started off with 8 bits, what you can do is this. You can say, for example, byte R is equal to byte I. Now what's going to happen is you will start with 64 that is stored in A, which is a byte variable, and you perform the left shift operation. And what you did was you left shifted 64 by 2. And since you know that left shift works with integer, you stored it in a variable which is of int type, but that will give you bits from 0 all the way up to 31. But what you want is from 0 to 7, which is the case for byte type. So what you did is you converted that to byte and stored it in a byte variable by doing this. This is called typecasting, and there's a few more things to discuss related to typecasting, but we're going to do that in a separate video. For now, let's just take a look at this example. So over here, let's comment these two out. Let's say byte A is equal to 64, and I'm going to say int I is equal to A left shift 2, and then I'm going to print the value of I. And if I run the code, what do I expect? 256, right? Because this is 64 multiplied with 2 square. And I just realized that I didn't discuss the trick that we did for the right shift. So coming back here, when we go for left shift operation, you see we started with 18, we got 72. And 72 can be written this way. 18 into 4, which is equal to 18 into 2 square, which is equal to 18, or the value that we started off with multiplied with 2 power num, right? So right shift operator is this value divided by 2 power num. But the left shift operator is value multiplied with 2 power num. So if you have something which you want to apply with another number and that number happens to be a power of 2, you can go for the left shift operator. So coming back to IntelliJ, 64 right shift 2 will be 64 multiplied with 2 square, which is equal to 64 multiplied with 4, which is equal to 256. But what's going to happen if I have another variable, say r, and I say I? First of all, I'll not be able to assign a value because I is int and r is byte. So what I'll do is whatever we have discussed just now, I'll say byte here in brackets in this way. And if I take the print statement and print the value of r, let's see what do we get. We get 0. And this is happening because if I start with 64, what will the binary conversion be? It will be 1 at position 6. And the rest of it, that is 5, 4, 3, 2, 1, and 0, will be 0, right? Now, if I take just 8 bits, and in this, if I go for right shift 2, what's going to happen? Well, whatever is at position 5 will be at position 7, so we'll get 0. And whatever is at 4, 3, 2, 1, 0 will be at position 6, 5, 4, 3, and 2 respectively. And the last two, that is towards the right most, will be filled with zeros. And ultimately, we will have 0. But if we take, say, 32 bits instead of just 8, which is what will happen internally, what's going to happen? Well, in that case, we will have 8, we'll have 9, and then 10, and then 11, and then so on, all the way up to 31. And all of these will be 0, of course. Now, if I right shift by 2, whatever is at 6 will be at 8, right? It will not get lost, which is what happened when we took just 8 bits. And all of these will be here. And this 2 will be filled with 0. And all of these remaining ones will also be 0. So we have got 1, 1 at position 8, which means we have got 2 power 8, which is equal to 256. And that is why if we use integer, we will get 256. But if we use byte, which means we use only the 8 bits, we get 0. So far, we're done with these operators and we are also done with these 3 operators. Now we are left with these operators. And if you observe, these operators are just the compound assignment of these operators. We had bitwise and now here we have bitwise and equal to. We had bitwise or, we have bitwise or equal to, and so on for all of these operators that we have discussed here. Now, if you recall, something similar is also possible with arithmetic operators. If we say plus equal to and we use it this way, a plus equal to b, it means a is equal to a plus b. Similarly, minus equal to when used with a and b will mean a is equal to a minus b, and so on. And not just arithmetic operators, we had used that with logical operators as well. So similarly, for bitwise operator, this will be the usage. If I have, let's say, a OP is equal to B, this simply means A is equal to A OP B, right? Where OP is an operator. So if I say ampersand equal to, or the bitwise and equal to, and I go for A bitwise and equal to B, I will have A is equal to A and B. So what's going to happen is bitwise and operation will be performed on A and B, and the result will be stored back in A. The same thing applies to all of the remaining operators. For this, I leave the code to you. what I recommend you do is you first of all go for A and B, and then you say, for example, R is equal to A and B, and note the value of R in this case. Then you go for A bitwise and is equal to B, and after you are done with A bitwise and equal to B, check the value of A and see if it matches the value that was there in R. But keep in mind that going for and equal to or equal to or XOR equal to etc. will change the value of A because you're performing some operation on two operands and you're storing the value back in the variable A itself. So this brings us to the end of the video. I hope that I've been able to teach you something new and useful. If you have any suggestions, feedback or queries, feel free to put them in the comments. Thank you so much for watching and I'll see you in the next one.